Alright, going to start this lecture. This is Look What I Have Created. I Have Made Fire. This is a video lecture over talking about heat, talking about specific heat, and the quote that we have is that education is not the filling of a pail, but the lighting of a fire. So let's jump into our learning goals for this lecture. Number one, students will be able to differentiate between heat and temperature. We've talked about this a little bit when we talked about when we got into kinetic energy and kinetic molecular theory and talked about gases. We're also the second thing is students will understand the relationship between heat and temperature with the equation Q equals mc delta T. Now what we're going to be doing here is we have to be able to use that in math, manipulate that equation, and solve for every single variable. So let's look at what we already know. Number one, that heat is a type of energy. We talked about this. Kinetic molecular theory again states that temperature is related to kinetic energy. Specifically, we want to look and we should know that energy can be transferred between objects. So any type of energy can be transferred. Now, what we learned in the lab, when the bolt was placed in the water, heat was transferred. The heat was transferred from the bolt into the water, and the amount of heat that was lost by the bolt was gained by the water. And so we see that that heat or that energy was conserved. Now the amount of heat is related to the temperature of the Bunsen burner, and we did some math to work back to try to figure out what was the temperature of the Bunsen burner. Now, heat in general, what heat is? Heat is the transfer of energy between two objects of different temperatures. Okay, so heat is specifically the transfer of energy. Now, heat will always flow from high to low. So from high temperatures to low temperatures. And heat can result in an increase in kinetic energy, temperature, or potential energy, which is change in phase. And we're going to talk about what this means later when we look at a graph, but we should know what a phase is. Phase, we're talking about a solid, a liquid, a gas. That's a phase that we're talking about. And then lastly, energy is measured in joules, which we see the conversion that we have here, 4.184 joules equals 1 calorie. That's the unit that we have when we are measuring. We see a lot of things in calories. We don't usually see a lot of things in joules. So, moving on, thermal equilibrium. Now what this means is that energy is transferred when atoms of high energy collide with atoms of low energy. We can say that objects in thermal equilibrium are the same temperature. This is an important concept. In the lab, when we put the really hot bolt into the water, eventually they both became the same temperature. That's thermal equilibrium. The example that we have over here is that if you have this 100 degrees Celsius and 0 degrees Celsius blocks, and you put both of those together, they will eventually reach thermal equilibrium if they're the same mass. If they're the same substance, then you'll reach a thermal equilibrium. And so what we see is that energy is transferred when atoms of high energy collide with low energy. So what's happening on a molecular level is that one atom will hit another atom, kind of like a billiard ball, and transfer some of that energy. So let's go ahead and from here jump into our first example. Now in our first example, it says, example A1, it says a can of hot soup is placed on a windowsill to cool. Describe what is occurring at the microscopic level. So when we think about the molecules, when we think about the very small pieces, what is happening to the energy? Well, eventually what we see is that in this, the soup is really hot, so therefore it's moving really fast. And so since it's moving really fast, you have these air particles all around that are moving as well. And what happens is they eventually end up hitting um, some of the soup, and so therefore what happens is it transfers the energy, and so the hot soup will hit into the air molecules, and the molecules will speed up, and the soup molecules will slow down, and so that's what we're looking for. Number or example A2, it says which has more thermal energy, a single cup of coffee at 80 degrees Celsius or a swimming pool at 10 degrees Celsius. Now, what we should be thinking here is that the thermal energy consists of both kinetic and potential energy. And so although the cup of coffee has a greater average kinetic energy or greater temperature, the amount of energy in the pool still exceeds that of the cup of coffee. So basically, the energy that is stored in that pool, even though it's at a smaller temperature, is much greater. Why? Because there's a huge difference between the mass of a cup of coffee and the mass of the pool. Jumping on down to A3. It says a single tub of popcorn at the movie theater can have 3,200 calories. And when we talk about calories with food, we're really talking about kilocalories. And so when you see calories on the back of any type of food, that really means kilocalories. And it says, how many joules is this? Well, we need two conversion factors. Once, since this 3,200 is in kilocalories, we first need to get that to calories, which we just know that 1 calorie equals, I'll take that away, it looks kind of like an I, equals our 1,000, sorry, one kilocalorie is 1,000 calories. Okay. And then what we can say is that our conversion factor that we had before, that we said that 4.184 joules equals 1 calorie. Okay, so we just set this up and do dimensional analysis, and we say that our 3,200, and that is kilocalorie, and 1 kilocalorie is 1,000 calories, and 1 calorie is 4.184 joules. We go ahead and work this out, and we'll get something right around 1.34 times 10 to the 7th joules. Let's go ahead and jump into phase transition graphs. Now, we can talk about these specifically because we said earlier that heat sometimes results in a change in temperature or change in the average kinetic energy, or it's the change in phase. And we need to be able to know this graph, see this graph. What this means is that we have our temperature on our y-axis, and this would be time on our x-axis. And what we see is that the temperature, as the temperature increases over time, what we see is it goes up, and then eventually what happens is that we're applying heat the entire time. Heat can be added, and basically what we see is heat can be added, no change in temperature. So we get this plateau, and so heat is added over a period of time, and we get that plateau right there. Now, and then we see we have this other slope, and then we have a plateau, and then we have another slope, and what we see is we see 3 slopes, 1, 2, and 3, and then we see 2 plateaus. So here's a plateau, and here's a plateau. Now, what's happening at the plateaus is that you're adding energy, and you're adding heat to the system, but you don't see a change in temperature. And so what this means is at the plateaus, you're changing phase. So the energy goes into changing from here, so at the first one, so we'll label that A, that first green slope that I circled, that would be heating up a solid. And then at the first plateau, right here, that is when you would change from a solid to a liquid. So that would be melting. Then you would have this slope right here. That would be the heating up of a liquid. And then you get to this plateau, and you would have changing from a phase from a liquid into a gas. And then this last slope would be the heating up of a gas. Now, where the energy goes, you might think, well, what about the law of conservation of energy? Energy can't be created or destroyed. Well, what happened is that energy goes into separating those bonds between the molecules. And so it separates them out so that they're able to move from a solid to a liquid to a gas. This phase transition graph is a good thing to remember and write down. Now, we'll go over the basics, going from a solid to a liquid. And going from a liquid to a solid. So what we call fusion, we normally call it freezing, requires the loss of heat. We see that this is exothermic transition from a liquid to a solid. We'll talk a lot more about exothermic, endothermic. Exothermic just means that that heat is being let go from the substance from the system into the surroundings. Then we have melting, where melting requires heat input. It's endothermic, and it's transition from a solid to a liquid. Now, heat required to fuse is the same magnitude of energy required to melt. So basically what it means is the same energy that it's required to freeze is the same energy that's required to melt. It's the same amount of energy, it's just what direction is that heat going. Next is gas, liquid, liquid, gas. And so condensation happens, it requires a loss of heat, so it's exothermic, and it's a transition from a liquid to a gas. Vaporization, or what we commonly know as boiling, requires the input of heat, and it is endothermic, and it's a transition from a gas to a liquid. And again, we're stating that to boil or to condense is the same amount of energy, it's just going in a different direction. So condensation is the loss of heat. Boiling requires heat. It's a different direction, but it's the same amount of heat. Then we have a gas. Sublimation, gas to a solid. We see that a sublimation requires the loss of heat, and it's exothermic. It's transition from a liquid to a gas. And then crystal lattice formation requires heat input. It's endothermic, and it's transition from a gas to a liquid. Again, energy is conserved in this, and that the same amount of energy it takes to sublimate is the same amount of energy that it requires to form that crystal lattice formation. Okay, what else affects phase? So let's look at this. When we're looking at this, this is a phase diagram, this graph over here, and we need to know the very specific things about it. The reason why we see it is we see this because now, instead of just looking at temperature and time, or temperature and heat input, what we're looking at is pressure and temperature. Okay, the states of matter is related to the volume, temperature, and pressure of a substance. So the reason why something is a solid is because of the volume, temperature, and pressure. We showed the relationship of these things in this phase diagram. And so what we see here, we can see it's labeled that is a solid, that is a liquid, and this is a gas. So at a specific pressure and temperature, you'll have a solid. At a specific pressure and temperature, you'll have a liquid, and at specific pressure and temperature, you're going to have a gas. So, how do we read it? Let's jump on down to the next slide, and it says, how do we read the phase diagram? So we already labeled where the solid, the liquid, and the gas is. Here's the solid, here's the liquid, here's the gas. Now phase changes, where phase change happens, normally you're not going to have changes in your all three, pressure, temperature, and volume. So usually if your pressure is held constant and you take this across, at this temperature right here, at this pressure, you got a solid. And then what happens, you increase that pressure, you move from this point right here, you have your melting point. And then you move into a liquid. And then what you have is you have your, going from a liquid into a gas, you have your boiling point, okay, or vaporization. And so this is the normal change. So going from solid to liquid to gas. We can see here we can go from a solid, we can go from our solid straight into our gas, that's sublimation, and back and forth there, but that's the normal transition. The critical point, also known as the critical state, undergoes and happens under very specific conditions, and at which no phase boundary exists. So after this critical point way up here, it's kind of just, it's in between phases. There's not a real boundary. It's a liquid, it's a gas, it's kind of moving all around in there. Triple point's a very interesting thing. Triple point is what happens when you, right here, and at this specific pressure, and you can see that they labeled it right here, it's right there labeled, at that specific pressure and that temperature, the triple point means that you have every single phase existing at the same time. So you have a solid, a liquid, and gas. So you can think of it this way: in a single test tube, you would have boiling water, liquid water, and ice all at the same place, same time. Okay, so let's jump into our example B1. What we see here is it draw a phase transition graph of a substance that has a boiling point of 124 Kelvin, a melting point of 23 Kelvin, and describe how the substance would be stored in the lab. So when we're looking at this, the phase transition graph, we have our temp over here, our time and heat input. This would be our heat input. And so what we would see is, remember, on all of these you're going to have one, then you have a plateau, slope, plateau, slope. Now remember, at each plateau, the first plateau is you are melting. So that's our melting point. So I'd label that 23 Kelvin. Our second plateau, that is your boiling point. So I'd label that 124 Kelvin. And if we were doing this for a lab, we would measure out with a ruler and everything else. So what we see is that. Now this at 24 or 124 degrees Kelvin, how would we store this in the lab? Well, at 124 degrees, we take that into Celsius. It's going to be a very negative Celsius, so it's going to be very, very cold. So this substance is going to exist as a gas, and so therefore we would have to store it as we would store gas in a container. Jumping down to example B2. Looking at B2, it says draw a phase diagram of a substance that does not sublimate. So when we're looking at this, what we would do is, this is a phase diagram. So now this is pressure and temperature. So it does not sublimate. So it does not go from a gas into a solid straight into a gas. So what we would see is we would see something that looks like this. This would be our solid, this would be our liquid, and this would be our gas phase. So there's no point here where we could go that we wouldn't pass through the liquid phase, and so therefore at no pressure or temperature is there anywhere we could go from solid straight into the gas. It's always solid, liquid, and then gas, and so there's no sublimation of this substance. Alright, looking at specific heat capacity, we're going to look at this definition. What it is the measure of energy required to change 1 kilogram of substance by 1 degree Celsius. Normally we measure these in chemistry. We don't use kilograms. We're going to use grams. In physics, we normally use kilograms. So we just have to make sure we pay attention to the unit that we have. Is it in kilograms or is it in grams? What specific heat basically means, think of it this way. We make pots and pans out of metal because they change temperature easily. How would cooking be different if you made pots and pans out of wood? Well, wood doesn't change its temperature as easily as metal. And so what we would see was it would take longer to heat up, and normally you would end up burning the wood before actually getting it to a proper temperature to cook. And so when we're thinking of specific heat, we're thinking about how easy or how hard is it to change the temperature. Um, Specific heat capacity trends. Solids have high heat capacities. Liquids are about medium heat capacities. Gases are very low. Water is the exception to this. Water is definitely the exception. It has a very high specific heat, and it allows for us to transfer a lot of energy to it. This is how basically your body cools itself with sweat, because water takes so much energy to heat up, so that all your energy from your heat is being transferred into that water and it cools you down. The equation for specific heat is Q. Q is heat. It's the energy transfer between objects of different temperatures. It is measured in joules. And then we have M, which is mass. Mass is the amount of matter. In chemistry, we're going to measure that in grams. We're not going to measure that in kilograms because we deal on a very micro scale. Specific heat is the energy required to raise 1 kilogram, or that CP, and P means specific pressure, that's the amount of energy required to raise 1 kilogram of material 1 degree Celsius or 1 degree K. And then we have the delta T. And I'll expand on that a little bit. Delta means change in, so temperature final minus temperature initial. That is what delta T means. And it's the change in temperature. So let's jump on into an example, C1. It says, describe the circumstance necessary for heat to be negative. So when we're looking at this one, we're trying to describe when will heat be negative. When will this Q be negative? And the answer for this is think of your temperature final minus temperature initial. So if your initial temperature was really big, say that it was 90, and your final temperature was really small, let's say that it was 10. The difference of this is going to be negative 80. And so you're going to get a negative delta T, which in the equation MC delta T, if delta T is negative, you're multiplying everything else by a negative number, then you have a negative Q. So anytime something cools down, you're going to have a negative Q. Next example, which object will undergo the greatest temperature change assuming equal masses? So when we're looking at this, is the greatest temperature change. So what's going to change the temperature the easiest? Well, it's going to be the one with the lowest specific heat. If we have a really low specific heat, that means our temperature changes really quickly. If we have a high specific heat, that means our temperature changes slowly. So the lower the specific heat, really fast change. The higher the specific heat, that means that it's resistant to changing temperatures. And let's jump into C3. It says, determine the final temperature of 1 kilogram sample of water if the sample is initially at 273 K before being subjected to 100,000 joules of heat. Okay, now we're going to say, using this, our equation that we use, or our C, Q equals MC delta T. We see that we have our Q, we have our temperature, okay, and this is our initial temperature, and then we see that we have the mass of the sample. So all we need is our specific heat, and then we can solve for it. So our specific heat of water is 4.18, and that's joules grams degrees Celsius, and so we need this kilograms into grams. We just multiply that by 1,000. So our equation worked out as Q equals MC parentheses temperature final minus temperature initial. And we're solving for our temperature final. So to solve this, we would have our 100,000 joules equals a mass of 1,000 grams times the specific heat of 4.18. We'll scoot that over. 4.18 temperature final minus 273, because that's our initial temperature. So we go ahead and solve for this algebraically, and we will end up with our 1,000 times our 4.18, so we'll divide both sides by that. Divide by 1,000 times 4.18 gets these guys to the other side, and then we're just left with this. And then all we do to solve the rest of this after we divide all of that out is we add 273, and that will give us temperature final, which our temperature final should be right around 297 Kelvin. Now, looking at heat and energy, the law of conservation of energy requires that energy must not be created or destroyed. And so what this means is that heat gained, we're looking at this picture over here, and we're pretending there's a fire. So the heat gained by the soup right up here, must come from the heat lost by the fire. And so we get this version of our equation that we had before, where the Q, the negative Q is hot, equals the positive Q, the cold. Because what happens? The heat from the fire is lost, so therefore it's negative, and it's gained by the cold soup, which is their positive. So let's go ahead and we're going to use this concept and jump into an example. Now, it says that a 500 milliliter sample of 100 degrees Celsius water is mixed with 10,000 milliliters of 10 degrees Celsius water. What will be the temperature of the water, or what would the temperature of the water be when the two samples are mixed? So what's going to happen? Well, the energy from the hot is going to be transferred into the cold. So this Q negative equals positive Q. Okay? Now they're both water. So what we can say of this is, remember the equation Q equals MC delta T. Same Q. So what we can say is negative MC delta T equals positive MC delta T. This is our equation that we have. Now, since both of the samples are water, it's a 500 milliliter sample of water and a 10,000 milliliter sample of water, they're going to have the exact same specific heats. So what we can do to save us a little time algebraically is just take those guys out, because when we use those, they're just going to go away. So this is what we have. What we're solving for. Eventually what will happen is that they will both reach the same final temperature. Okay, so what we'll have is we'll have our negative, our first math, this is a 500 milliliter sample, and water has a density of 1 gram per milliliter. So we can say that this is 500 grams times our temperature final minus our temperature initial, which is 100 degrees Celsius, equals our 10,000 gram sample, because remember 1 milliliter equals 1 gram, times temperature final minus our initial temperature of 10 degrees Celsius. Okay. Now when we're solving for this, distribute, and then solve for temperature final. If you do this one right, what you'll see is that your final temperature will be 14.3 degrees Celsius. That will be your final temperature, because this sample will only raise that sample just a little bit. Next example, it says that a blacksmith is making a new axe for a customer. The axe has a mass of 5 kilograms, is made from iron, and it gives us our specific heat, and was heated to 1500 degrees Celsius in order to shape. What will the final temperature of the axe be after it is plunged into a 100 kilogram tub of water at 23 degrees Celsius? So again, this is our Q minus equals Q positive. So to work this one out, we have to set it up where our negative MC delta T equals positive MC delta T. And so on this, we want to know what will the final temperature of the axe be when it's plunged in. Temperature final will be the same. So it's just like our other equation. So negative our mass, what's going to be losing the heat? Well, what's going to be losing the heat is going to be the iron. Okay, so we take our negative, which our mass is, it says that it's 5 kilograms, so it's 5,000 grams, times the specific heat, which for iron is 0.46. So we get our 0.46 for our specific heat, times our temperature final, minus our initial temperature, which of iron is 1500 degrees Celsius, equals our mass of our water, which it's 100 kilograms, so that is going to be 100,000 grams, times a mass of our or that's our mass times the specific heat of 4.18 times our temperature final minus 23 degrees Celsius. And from here, what we'll do is we'll take this, multiply those, distribute to everything within the parentheses, and then we will solve for our temperature final. And when we solve for our temperature final, we should get something right around 31.1 degrees Celsius. And our last example, it says a 1 kilogram platinum, and it gives us the specific heat. We'll change it to grams, so it's just 0.130 block, is heated in a container in which all of the heat from the combustion of ethanol goes into a platinum block under adiabatic conditions. The platinum block is plunged into a 1,000 kilogram water bath initially at 20 degrees Celsius. The temperature is allowed to equilibrate with a block remaining at 18 degrees Celsius. What is the mass of the ethanol combusted? Ethanol produces 1,300 kilograms of heat per mole. So when we're working this one out, what we can see is the first thing that we would do is that all of the heat is transferred into the block, and then what we do is it would transfer into that water. The platinum is transferred into that water. So it's 1 kilogram of platinum is heated. And so what we see is that we have the change in temperature. Initially at this, the temperature is allowed to equilibrate, and it goes to this. And so what we're looking at is if we have the mass of the water, we know the specific heat of water, and we have the change in temperature of water, we can find our Q. So Q equals our mass, which is here we're going to say that it's 100,000 grams, times our specific heat of 4.18. And our change in temperature from 20 degrees to 18 degrees. It says at 20 degrees the temperature is allowed to equilibrate with the block at 18 degrees. So what we see is that this is our – change in temperature is 2 degrees Celsius. So not a lot of change in temperature, but it is some. And so we get our Q, which is going to equal right around 836,000 joules. And since what we can see is that it produces 1,300 kilojoules of heat per mole, what we can say is we can figure out how many moles we're going to have. So what we see is that when we change this from joules into moles, we see that we have our 836,123, and that is joules, and that is in kilojoules per mole. So we'll go 1,300 and then add 3 zeros to put it in joules is 1 mole. What we'll see is we'll get a mole of 0.64. Okay, that is how many moles of ethanol we have. And so to go from moles into grams, all we do is 0.64 moles. 1 mole in our ethanol is about 195.1 grams. Multiply that out and we should get 124.9 grams of our ethanol.